Okay, we're in section 4.5. I mentioned in the last video we'll likely have multiple videos here for this section. I thought I would just do one video per problem. These problems take some time because it's really kind of a complete summary of the things that we have learned in algebra and in trig and now in calculus, to be able to sketch a graph. The way that we are sketching the graph is we're going through a list of 10 steps here, these 10 steps. And of course this is in your notes, and I mentioned this on the last video there. So I'll be using this list, which is also what the book is doing as well. Okay. Here's another example. Let's graph f of x equal x divided by x plus 1, the quantity squared. Okay. You might see the terminology analyze this function. Okay, so what they mean by that is go through the list of steps that were there. So let's do that. Okay, the domain of f is step 1. X can't be -1. We know we can't divide by 0. Because I'm going to throw away -1, of course I'll know I'll have a vertical asymptote there at x equal -1. Step 2, we want to find the intercepts. Okay, so the x-intercepts, when you set the function equal to 0 and solve, multiply both sides by the denominator there, and you get x equals 0. If you plug 0 into the function to get the y-intercepts, you get 0 as the output. So 0, 0 would be the one and only intercept on this curve. Step 3, we want to check for any symmetry. Okay, if f of -x and f of x are the same for all x, then f is an even function and would be symmetric to the y-axis. That's not going to happen here because if I replace x with a -x, I don't have exactly the same function as I originally had, right? Because I have a -x divided by -x plus 1 squared. That's not the same as what we see there. F is not even. Okay, now is f odd. Well, for f to be odd, then f of -x and negative f of x would have to be the same. And that would mean that the graph was symmetric to the origin. Well, if I replace x with a -x, that would not be the same as just throwing a negative in front of the function. I'd have -x in the numerator, right, but I'd still have a -x plus 1 squared in the denominator, and those wouldn't be the same expression then. So there's no symmetry in this situation. That's fine. I mean, the majority of the functions that you guys would ever work with, there's not going to be any symmetry. Okay. Let's take a look at step 4. Step 4, we want to find all the infinite limits and limits at infinity. Okay, now I've already thrown away -1, so I should be looking at one-sided limits around that number. The limit as x approaches -1 from the left of f of x is what? Well, if I'm on the left side of -1, I'm going to have a negative in the numerator, and no matter what, I'm going to have a positive in the denominator, right, since I'm squaring the denominator there. And so negative, and of course if you're close to -1 on the left, you're going to have a small positive in the denominator. A negative divided by a small positive is a large negative. Okay, now how about if I'm on the right side of -1? Well, if I'm on the right side of -1, but close to -1, I'm still going to have a negative in the numerator. I'll have a positive in the denominator no matter what, since I'm squaring the denominator there. A negative divided by a small positive is going to produce a large negative output. Okay. How about the limits at infinity? So the limit as x approaches infinity of x divided by x plus 1, the quantity squared. You can use L'Hopital's rule on that since you're in indeterminate form, infinity over infinity. And so that's what I've done. You get the limit as x approaches infinity of the derivative of the top is 1 divided by the derivative of the bottom. That'd be a chain rule. You're going to have 2 times x plus 1 to the first times the derivative of x plus 1 is 1. X is approaching infinity, so the denominator is going to be growing without a bound as the numerator just sits at 1, and you get 0 then as the output. How about the limit as x approaches negative infinity of x divided by x plus 1 squared? Well, that's going to be pretty much the same sort of calculation, right? You'll use L'Hopital's rule to begin, and the denominator is going to be growing without a bound in the negative direction, as the numerator just sits at 1. So the output values, the y values, are going to be getting very minuscule. They'll be negative numbers, but they'll be getting closer and closer to 0. So we're going to have a vertical asymptote at x equal -1. Either one of these two infinite limit calculations would tell us that. But that's something that we already knew from earlier. You know, you're throwing away -1 in the denominator, so we're going to have a corresponding vertical asymptote at that spot. We already know that from algebra. And we'll have a horizontal asymptote at y equals 0. Either one of these two limit calculations would tell us that, but of course from algebra, if you have a rational function, which we have here, and you compare the degree of the top to the degree of the bottom, if the degree up top is less than the degree of the bottom, y equals 0 will always be a horizontal asymptote. Now that's what we see here. We have a degree 1 up top, there's a degree 2 down under. If I were to FOIL this out, the leading term would be an x squared, right? And so since the degree of the top is less than the degree of the bottom, y equals 0 is a horizontal asymptote. Okay, step 6, I need to find the first derivative and get all the critical numbers. Well, f prime of x would be a quotient rule. Also within that, there's going to be a chain rule. And so we're going to have the bottom is x squared plus 1, x plus 1 squared times the derivative of the top, that's 1, and then minus the top is x times the derivative of the bottom, that's 2 times x plus 1 to the first times 1, and then all over the denominator squared. X plus 1 squared would be x plus 1 to the fourth. Okay, and then you'd want to simplify that. To begin simplifying, x plus 1 is in common to these two terms in the numerator. Let me go ahead and factor that out and cancel it with one of these 4 in the denominator. When I do that, I'm going to have an x plus 1 cubed in the denominator. Okay, so one of these x plus 1 terms have been factored out and canceled. There's going to be one more then from that. This x plus 1 has already been factored out and canceled, so I'll be subtracting 2x then from the second group. X minus 2x is negative x. When you set this equal to 0 now, multiply both sides by the denominator. That'll clear out the fractional form there. And if you add x to both sides, x equal 1 would be the solution to that equation. 1, therefore, is a critical number. -1 is another important number that I'd use in the table. That's not a critical number because -1 was not in the domain of the function. Remember, a critical number has to be in the domain of the original function. But when we make our table, we want to include any critical numbers along with any numbers producing vertical asymptotes on the graph. So I still want to make sure that -1 is there. Okay, and that's going to split the real number line into 3 sections. I've got my 3 intervals arranged. Step 7, we're using the first derivative test here, of course. And so now I'm ready to choose my test values. I'm going to choose -2 in the first group. If I plug that into f prime, I'm going to get 3 divided by -1 cubed is -3 is the output. That's a negative, so that means that we're decreasing on that part of the graph. If we let x be 0 in the middle interval, we're going to get 1 divided by 1 is 1. So we're increasing there. And if we let x be 2 in the last group, 1 minus 2 is -1 divided by 3 cubed is 27. And so that's a negative there. We're going to be back decreasing again. Okay, we're increasing and then decreasing. That's going to produce a local max on the graph at x equal 1. When x is 1 and we plug that into the function, we're going to have 1 divided by 2 squared is 4, so 1/4 would be my y value. We're decreasing and then increasing, but that's not a local min, right? Because -1 is not in the domain of the function. We know we have an asymptote there. But we still know what's happening around that vertical asymptote. Okay. Step 8 is to calculate f double prime, and so I've done that. We're going to use the quotient rule on f prime along with the chain rule when we differentiate the denominator. And okay, so it's going to be the bottom times the derivative of the top, that's -1, minus the top So 1 minus x times the derivative of the bottom, that'd be a chain rule. You're going to have 3 times x plus 1 squared times the derivative of x plus 1 is 1, all over the denominator squared. X plus 1 cubed squared would be x plus 1 to the 6th. And now you'd simplify that. To begin simplifying this, I see there's an x plus 1 squared in common to these two groups. Okay, so I'm going to factor that out and cancel it with one of these 6 terms that are in the denominator. After I do that, there's going to be 4 x plus 1 terms left in the denominator. Okay, and in the numerator, then I'm going to have x plus 1 times negative 1, that'd be negative x minus 1, and then minus, so this x plus 1 squared has already been factored out and canceled. So you got minus the quantity 1 minus x times 3. You can distribute the negative 3 into those two terms there. That'll give you a minus 3 plus 3x then at the end. Okay, combine your like terms. Negative x plus 3x is 2x. Negative 1 plus minus 3 is negative 4. And if you set that equal to 0 now, multiply both sides by the denominator, add 4 and divide by 2, and you get x equal 2 then as the solution to that equation. So now I'm ready to set up the concavity test, this table here. Of course, 2 is going to go on the number line. And I'd still like to know what's happening around x equal negative 1, okay, as far as concave up or concave down. So I still want to make sure I'm using negative 1 here in this chart as well. We got interval, number chosen, value of f double prime, and then our conclusion. Here's my intervals splitting up the real number line about these two numbers here. And I'm ready to select my test values now. So like if x is negative 2 and I plug that into f double prime, I'm going to get, let's see here, negative 8 divided by negative 1 to the 4th is 1. Okay, negative 8 over 1 is negative 8. That means I'm concave down on that part of the graph. If I let x be 0 in the middle section there, plug that in, I'm going to have negative 4 divided by 1 is negative 4. We're still concave down, it looks like. And then we'll use 3 as a test value for the third interval. If I plug in 3, I'm going to have 2 times 3 is 6, minus 4 is 2, divided by 4 to the 4th is 256. Okay, so I'm getting 2 divided by 256. That's a positive, so we're concave up. We switch concavity once. We switch from concave down to concave up. And so we're going to have an inflection point at x equal 2. When x is 2, and you plug that in here, 2 divided by 3 squared is 9, so 2/9 would be the output. Okay. Now, of course, this should go without saying, but make sure that when you're asked to identify like an inflection point or a local max or a local min, state it as a point. Okay, don't just write x equal 1, okay, or x equal 2 or something like that. No, I want to know the point, okay, because I'll have students, not get the correct y value there. They didn't plug it in the right spot or they didn't calculate correctly. So be sure that you've stated that point clearly, whatever it is. Now I should have plenty of information here to begin sketching this graph. I'm just going to kind of run through the information again and get it on the picture. We're graphing f of x. Here's the domain. All real numbers except for negative 1. Since we're throwing away negative 1, we've got a vertical asymptote there at x equal negative 1. We've only got one intercept on the graph right here at 0, 0. There's no symmetry on the graph. Okay, we've computed our infinite limits. If you're on the left side of 1, if you're on the left side of negative 1, and getting closer to negative 1, the y values are getting big in the negative direction. Same thing on the right side of negative 1, the y values are getting big in the negative direction. So this curve is going to be heading downward on both sides of the vertical asymptote there. As you approach infinity or negative infinity, the y values are getting closer and closer to 0 on either side. We can see that. And okay, we've already, x equal negative 1 is a vertical asymptote. We already had that there. Y equals 0 is a horizontal asymptote, right? The graph will cross the horizontal asymptote once. We can see since 0, 0 is on the graph. Okay. Okay, we found our first derivative, and through the increasing and decreasing test, we found that there's a local max at 1/4, so that's about right there. Try to make it so there's a little hill there. Okay, it's maybe tough to kind of squeeze that in, but that's a local max. And then calculated f double prime, we use the concavity test, and there's an inflection point at 2/2/9. Okay, now 2/2/9 is right here. That point is a little bit lower than the previous one, right? Because here's a max point, it's the highest point in the neighborhood. Try to make it look like this point is a little bit lower than that one that is to the left. Okay, and on the, of course I can begin drawing this curve now passing through these points. I've already got 3 points here to work with. The curve was heading downward and outward here, getting closer to this asymptote, so we're going to have a slight bump in the graph there at that max. And on the left side of the vertical asymptote, we already said that the curve is heading downward. And it's heading outward here, getting closer and closer to 0 if x is approaching negative infinity. I just plotted like 2 additional points just to have a more accurate thing. It may be the case that at the end you might need to plot like an additional point or 2 just so that the picture is more accurate. So consider that. Like here, if I were to let x be -2 and I plug that in, -2 divided by 1 is -2. Okay, so here's -2, -2 on the graph. If I let x be -3, -3 divided by -2 squared is 4. Okay, so here's -3, -3/4 is on the graph. And of course the curve has to flow with those 2 boundaries there. All right, so that would be just a quick sketch then of the graph of this function.